I'm going to begin section 5.6 now. 5.6 is all about solving exponential and logarithmic equations. And now we've already been solving exponential equations a little bit. We did that in section 5.3, although I did mention there was more to know about solving an exponential equation. But I'm gonna begin with logarithmic equations and just show you a bunch of examples here. So in this first example, I want to solve this equation for x. Now, when you're solving a logarithmic equation, usually the plan is going to be using your properties of logarithms or using the definition at some point in the calculation. Okay. So I'd like to lose the logarithmic notation here to begin. And let's use the definition. So remember, y equals log base a of x means x equals a to the y. Okay, I'm going to go ahead and rewrite this logarithmic form into an exponential form. 4x minus 7, that's my input, so that'll be all alone on the exponential. 3 is the base, that's the base of the exponential. 2 is the y value, so that'd be the power of 3. And see, this puts me back on familiar ground now because now I'm looking at just a linear equation. 3 squared is 9. Add 7 to 9, you get 16. 16 equals 4x means that x is 4 when you divide both sides by 4. Okay, now one thing that you always have to do when you're solving a logarithmic equation is you got to check your answers for any extraneous solutions. I had mentioned in another video that in all of algebra, there's really only 3 equations where you have to be checking your answers for extraneous solutions. We saw 2 of them in chapter 4. That was a rational equation and then a radical equation. Here's the third kind, logarithmic equation. So you can sometimes have extraneous solutions come up. Be sure to check those numbers. Okay, now when you're checking, the first thing that I'm always looking for is that the overall input value is a positive. Okay, now 4 is positive, but that's not what I'm saying. Does the overall resulting number still end up being a positive? Well, 4 times 4 is 16, minus 7 is 9. 9 is a positive. Okay, so that looks good. Now, the next thing that I'm looking for is to know that I'm correct here by using my properties of logarithms. Okay, so is it true that log base 3 of 9 is equal to 2? Well, log base 3 of 9, that's the same as log base 3, 9 is the same as 3 squared, right? And I know powers can come out of logarithms. And I also know log base 3 of 3 is 1. So 2 times 1 is 2, and 2 is also the number that I see there. 2 equal 2, that's true. So 4 would be the correct answer there. Okay, here's another example. I want to solve for x. Let me get the logarithmic terms onto one side. And I know that if I'm adding logarithms where I've got the same base, I can combine that to a single logarithm by multiplying the inner terms. 4x times x is 4x squared. And so then at this point, I would plan to use the definition of a logarithm in order to lose the logarithmic notation. 4x squared is my input, so that's going to be all alone in the exponential. 2 is the base. 2 here is the y value, so 2 squared would go on the other side. Divide by 4, and you got x squared equal 1. Take the square root of both sides, so x would be plus or minus 1. Now, I don't want both of those because negative 1 is going to be a problem, and that I know I can't take log of a negative number. So negative 1 would be extraneous. 1 is going to be kept though. Okay, now log base anything of 1 is always 0. So I've got 2 minus 0 is 2 on the right. On the left, if x is 1, I'm looking at log base 2 of 4. Well, log base 2 of 4, that's the same as log base 2 of 2 squared. And again, powers can come out of logarithms, right? Log base 2 of 2 is 1, so I got 2 times 1 is 2, and yeah, 2 is also the same number there on the right. So x equals 1 is going to be kept. Negative 1 would be extraneous. Okay, here's another example. Solve for x. Now, the 2 that is in front of the logarithm on the right, I can bring that inside as a power on the inner part using law 3 on that list of laws of logarithms that I gave you. And now I've got the natural logarithm on both sides here, and I've taken care of the multiplier there. Whenever you have a logarithmic equation and there's logarithms on both sides with the same base, like what we see here, you can get rid of the logarithmic notation and set the inner terms to be equal. So I'm doing that on the next line. X plus 1 equal x minus 1, the quantity squared. And x minus 1 times x minus 1, when you FOIL that out, you're going to get x squared minus 2x plus 1. If you subtract 1 from both sides, those terms are gone. And if you subtract x from both sides, then we have x squared minus 3x equals 0. That's a quadratic. And x is in common to these two terms. You can factor that out. Set the factors equal to 0, and you'll have x equals 0 or x equals 3. Be sure to check those. 0 is not going to work because if I plug that into the original here, you can't take log of a negative, so throw that number away. 3 is going to be fine, though, because you're going to have ln 4 on the left, and then 2 ln 2. Well, the 2 can come up as a power of the inner part, so it'd be the ln of 2 squared, or the ln of 4. ln 4 equal ln 4, that's true. So 3 is going to be kept, and 0 would be extraneous. Now, when you're checking your answers, be sure that you're plugging the numbers into the original equation. Always do that, okay? Like if I were to plug 0 into this line, or even this line, let's say, right here, I'll have 1 equal, negative 1 squared is 1, so 1 equal 1, like that's a true statement. However, 0 is extraneous because this equation here was not my original equation. Always plug the numbers into the original equation when you're checking those to see if you have extraneous numbers. Now, of course, a common mistake that I will see students make is they will forget to check their answers. You have to be doing that here. Make sure that you're remembering that. Okay, here's another example. Another logarithmic equation, solve for x. Okay, let me combine these two logarithms into a single logarithm. I'm going to multiply the inner terms there using law 1 on that list of laws that I gave you. X times x minus 3 is x squared minus 3x. Now, at this point, you have a couple of different options. You could use the definition of a logarithm, or you can get a little creative with it. If you use the definition of a logarithm, x squared minus 3x would be all alone on the exponential, and 4 is the base, so that's going to be the base on the exponential. 1 is the y value, and if you subtract 4 from both sides, that brings you to this line here. So, or you can get a little creative with it. 1 is the same as log base 4 of 4. And you've got log base 4 now on both sides. You can remove the log base 4 notation and set the inner terms to be equal. Subtract 4. So either way, you're still going to get to the same spot there if everything is done correctly. We have a quadratic equation, and this is going to factor. When you set the factors equal to 0, you get x equal negative 1 or x equal 4. Negative 1 is no good because you can't take log of a negative. That's going to happen on both of those. 4, let's see, we're going to keep 4 because log base 4 of 4 is 1. Log base 4 of 1 is 0. 1 plus 0 is 1. Okay, so 4 is kept, negative 1 is extraneous. And by the way, something else I wanted to mention here, just before we do this next problem. Some students will, for whatever strange reason, immediately cross off a negative. Don't do that. Okay, you still want to make sure that you're checking that the overall value inside the logarithm is not a negative. It didn't happen here, but if I plugged in negative 1, and let's say I had a positive overall value inside of both of these logarithms, like I'm keeping negative 1. Okay, So don't make that mistake. You know, we want the overall value not to be 0 or a negative. Let's take a look at this next one. This will be the last one I do for the video. So I want to solve for x. On the left, let me use law 2 to get a single logarithm. I'm going to divide the inner terms there. Of course, I'm using base 10 here in this problem. And at this point, I'm going to use the definition of a logarithm to rewrite this into an exponential form. That way I lose the logarithmic notation. Again, it's base 10, so 11x plus 9 over x plus 3, that's going to be all alone in the exponential. 10 is the base, 3 is my y value, so I'll have 10 cubed, or 1,000, on the right. So the next thing, if you multiply both sides by x plus 3, you'll get rid of the fractional form that's on the left there. 1,000 times x plus 3, when you distribute, would be 1,000x plus 3,000. If you subtract 11x from both sides and subtract 3,000 then from both sides, 11x minus, 1,000x minus 11x is 989x. And then I'm also subtracting 3,000 from both sides. 9 minus 3,000 is negative 2,991. Divide by 989, and that way x is all alone. Negative 2,291 divided by 989 would be roughly negative 3.02 if you were to look at the decimal form of that number. Now again, I'm not going to immediately cross that off because that's a negative, right? I still got to check my answer. So if I plug that into this guy here, let's say, the original, on the second term, negative 3.02 plus 3 is negative 0.02, and you can't take a log of a negative. So in fact, we are throwing this number away. This was the one and only number that came up as a possible solution, didn't work out. So there are no solutions to this equation here.